Welcome friends, Igor is here, and in this video we will apply an efficient method for computing determinants. In this lesson we will compute the determinant of a sample 4x4 matrix efficiently by using row operations. Let's get started. In the previous video we have established how applying row operations to a matrix affect its determinant. Swapping two rows of a matrix changes the sign of the determinant. Scaling one row of a matrix scales the entire determinant. Also, multiplying a row of a matrix by a scalar and adding the result to another row does not change the determinant of the matrix. We have this 4x4 matrix, and I will explain how to compute its determinant by first applying row operations to this matrix so that we reduce the matrix to the so-called upper triangular form. I will explain what this form looks like when we get to this part. We will apply one row operation at a time, and we will keep track of what happens to the determinant of the matrix A. To reduce this matrix to an upper triangular form, we will follow along the Gauss-Jordan elimination algorithm. This video explains how the algorithm works. Please check it out if you need a reminder on the Gaussian elimination. Let's start reducing the matrix. Our first task is to produce the entry of 1 at the top of column number 1. We can achieve this by scaling row 1 by 1/2, but this will introduce some fractions, so why not instead swap rows 1 and 2? So the first row operation we perform is the row swap, and the new matrix, I'm going to call the matrix A1, has determinant that is equal to the negative of the determinant of A. Next, we're going to use a sequence of row replacement operations to produce zeros below the leading one in row 1. First, we multiply row 1 by -2 and add the result to row 2, the new matrix I'm going to call A2, and compared to the matrix A1, the determinant did not change. Therefore, the determinant of the original matrix A is negative determinant of the matrix A2. Next, we multiply row 1 by 1, add the result to row 3. We get the matrix A3, and its determinant is equal to the determinant of the matrix A2. This is just a carryover of the last operation from the previous slide. The next step is to multiply row 1 by -3 and add the result to row 3. We get matrix A4, and the determinant did not change. We have produced zeros below the leading one in row 1, and the next part of the Gaussian elimination algorithm says forget about the top row, work with the submatrix that remains. We locate the leftmost non-zero column, which in this case is column number 2, and we need to produce the entry of 1 at the top of this row column. Notice, if we try swapping rows, then no matter which row appears in the position of row 2, scaling will introduce fractions. This is possible, you can do it this way. But instead, let's add row 3 to row 2. This does not change the determinant, but now we can scale this row 2 by -1/2. We obtain a new matrix A6. Because it was the scale operation, determinant of the matrix did change. And now please pay careful attention. I will explain why determinant of the matrix A is equal to 2 times determinant of the matrix A6. We scaled a row by -1/2, so it looks like it should be the previous determinant, which was negative determinant of A5 multiplied by -1/2, resulting in a scalar multiple of 1/2. Why is it 2, not 1/2 here? Well, it's because A6 is a new matrix, and the determinant of the new matrix is the determinant of the previous matrix scaled by -1/2. But in our expression, we write the determinant of the original matrix in terms of the determinant of the new matrix. Therefore, the old determinant is a multiple of -2 of the new determinant. We have produced a leading one in row 2, and now we need to produce zeros below this leading one. So the first operation is multiply row 2 by -4, add the result to row 3. This is a new matrix A7, and its determinant is the same as the determinant of the previous matrix A6. This is just a carryover from the previous slide, and the next step is to multiply row 2 by 4, add the result to row 4. We get matrix A8, and its determinant is the same as determinant of A7. We have produced zeros below the next leading one, so now we forget about this second row and we work with the submatrix that remains. This submatrix consists of rows 3 and 4. We locate the leftmost non-zero column, which in this case is column number 3, and again, we want to produce a 1 at the top of this column. Of course, you can scale row 3 by 1/2, but if you want to avoid introducing fractions is possible, then an alternative approach would be this. First, we're going to multiply row 3 by -1 and add this to row 4. The new matrix A9 has the same determinant as the matrix A8. Next, let's multiply row 4 by -2 and add this to row 3. The new matrix A10 has the same determinant as the matrix A9. And then we're going to swap rows 3 and 4. This results in the change of the sign of the determinant. And now, all that remains to do is to scale row 4 by 1/55. So, the determinant of the matrix A12 is equal to the determinant of the previous matrix A11 scaled by 1/55. But then, the determinant of the old matrix A11 is equal to the determinant of the new matrix A12 scaled by 55. And now we have reduced the matrix to the upper triangular form. Do you see why it's called upper triangular? All entries below the main diagonal are equal to 0, and the only non-zero entries appear in this upper triangle part of the matrix. In the classical Gauss-Jordan elimination algorithm, we would now have to produce zeros above all the leading ones, but there is no need to do this to compute the determinant of this matrix. In fact, the determinant of an upper triangular matrix is equal to the product of the entries on its main diagonal. So, the determinant of matrix A12 is equal to 1, and that means the determinant of the original matrix A is equal to -110. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss a remarkable class of so-called elementary matrices. I will see you later.